So to start off, we're going to work on this warm-up question. So let G be a graph of order n. If the degree of x plus the degree of y is at least n minus 1 for every two non-adjacent vertices x and y, then G is connected. So what we're going to do here is we're going to show that every pair of vertices either has distance 1 or distance 2. And because the distance exists, that means that the whole entire graph is connected. So let's start off with let x and y be in the vertex set of G. If x, y is in the edge set of G, then the distance of x and y is equal to 1, and so they are connected. All right, so what if x and the edge xy is not a part of the edge set of G? Then notice how that there are n minus 2 other vertices, and the degree of x plus the degree of y is at least n minus 1. What does this mean? This means that at least one vertex is connected to both x and y by the pigeonhole principle. So there is some vertex w in the vertex set of G such that x w and y w are in the edge set of G. And once again, that's by the pigeonhole principle. And so x w y is a path from x to y, so they are connected. And since x and y were an arbitrary pair of vertices from G, and we checked both possible cases where they are either distance 1 or they are not distance 1, we have shown that they are connected by either a distance of 1 or a distance of 2, meaning the entire graph is connected. Now, let's look at our real problem for the day. Okay, so the main problem today is this, and we're really just extending this to one more step. So let G be a graph of order n. If the degree of three vertices x, y, and z, if we sum up their degrees and it's at least n minus 1 for every three pairwise non-adjacent vertices x, y, and z, must the graph G be connected? And the answer is no. And so let me walk you through my process of how I got to this result. So I started off thinking about this problem, and I believe I needed some sort of complete graph, and we denote the complete graph with n vertices as kn. And so I was thinking, okay, what if I joined three kn's together? Then to pick any three non-adjacent vertices, or 3 pairwise non-adjacent vertices, means I need to have one from each one of these KNs, because within each one, they are all connected to each other, all the other points in each one of these subgraphs. So that means I would have a total of 3 times, and then each vertex would have n minus 1, and that's 3n minus 3, my bad, 3n minus 3. And so the problem says we need one less than the total number of vertices. Well, there's n in each one, so we wanted to get bigger than 3n but minus 1, and that's clearly never going to happen. So then I thought about, okay, what if I had a complete graph of size n, and then I added onto it the complete graph of size 1, which is pretty trivial, but then I realized this wouldn't work because now I have, I cannot find 3 vertices that are pairwise non-adjacent. That can't happen because at least 2 vertices must come from Kn, but those are all adjacent to each other, so we can't have that. So what I ended up discovering was, if I have the K4 as a subgraph, so here we go, here's K4, and then I went and added on a couple or a few other vertices, so I have these 2 here, plus a lonely vertex out here, and I connect them like this. And then this one goes here, here, and here. We can see, okay, a few things. One, it is impossible to have a 3 non-adjacent, or 3 pairwise non-adjacent vertices if one of the vertices has degree 5 right here. So one of these 2 circled in green. This cannot happen because these are connected to everything else in the picture, and so except for the lonely vertex over here, which means we cannot find, we can pick the lonely vertex, one of these, but we can't find a 3rd vertex, so we cannot choose either of these 2. Let's suppose we pick one of the vertices that has 4. Well, you can't pick the 3 that's next to it, and you can't pick the 4 that's next to that, that's adjacent to the other. You can't pick the other 4, vertex of degree 4, my bad. So you must pick the vertex of degree 3 that is not adjacent, plus the lonely vertex over here. Okay, and that's the exact same thing if I picked the other degree 4 vertex. So if I picked this one, I couldn't pick that, and I couldn't pick that. So I must pick these 2. Okay, but that's not the only option. We have one more option. We could pick both of the degree 3s and the lonely vertex out here. And we can see those 3 are non-adjacent. So no matter what, we must pick a degree 0, we must pick a degree 3, and our choice is either one of the degree 4s, whichever one is not adjacent to the current degree 3, or we must pick the other degree 3. Meaning, if no matter what, the sum, so degree of x plus degree of y plus degree of z. Sorry if I switched up the letters. What's it supposed to be? Yeah, x, y, and z. Degree of x plus degree of y plus degree of z must be, so we know for sure we must have a degree 0. We know for sure we must have at least one degree 3. And then either a choice of degree 3 or a degree 4. Well, the smallest it could be is a degree 3, which means the degree of x plus the degree of y plus the degree of z is at least 6. And then notice how there are 1, 2, 3, 4, 5, 6, 7 vertices, which is the requirement from the problem, the number of vertices minus 1. And so we know for sure that this is disconnected, but it satisfies, and so we have completed the problem.